Okay, so thank you everyone for coming to the second day on the workshop on modern techniques in Riemannian geometry slash the colloquium of geometry of the University of Yucatan in honor of our friend, colleague, and professor Oscar Palmas. And so it's my big pleasure to present again Professor Marcos Alexandrino from the University of Sao Paulo with his second lecture on holonomy and singular Riemannian foliations. Thank you so much,
Okay,
Professor.
thank you. Thank you, Jesus, again. Welcome, people. Welcome, Diego. So, again, thank you very much for the invitation. Again, congratulations, Oscar. It's really a pleasure. So, today we continue our lecture about holonomy and singular Riemannian foliations. But wait. Yes. Last time we talked a little more about more about the structure of a singular foliations. Today we should say a few words about connections, holonomy foliations, and the Ambrose Singer theorem. So my idea was to present some ideas of proof for students in lecture 1 and 2, and the lecture 3 will be really just a general talk with the current works, okay? Anyway, today we should start to give an example of non-homogeneous singular Riemannian foliations and review the ideas behind the proof of Ambrose Singer theorem that in fact somehow related with the semi-local model. Just to be sure, I would like to spend 5 minutes, maybe less, to review what I have done yesterday. Yesterday, we start with a nice motivations from geometrical control theory to motivate the concept of orbits and the singular foliations. I wanted to stress they appear natural in engineers, in economic sciences, and so on. But the main concept that we want to use from this nice area is the concept of orbit. Given a set of smooth vector field everywhere defined, that means the union of the domain is the manifold M. We'll call an orbit through a point Q0 all possible compositions of the flow for all elements of our geometric control system. That means just this set of vector fields, and for all time. The motivation, we give this motivation talking a little about a train traveling from one station to the other, and this is the concept that we should use. So recalling that a partition of M into immersed submanifolds is a singular foliation. It's a singular foliation if so you have here a kind of a partition if for each vector VP here we can produce an extension of this vector that coincide in P, is tangent to all the leaves, and this is done just in the neighborhood of the point. And why we have talked about geometric control theory? Because we have used it's important to us the Stefan Susman theorem that say when you have a geometric control system, then the partition of M into the opt is a singular foliation. So this is the kind of object that we present yesterday. We keep an example in mind. We consider to have always an example in mind. We consider or an action of a Lie group on a manifold, and then the vector fields were the infinitesimal actions, and the opts were the opts. we talk a little about attainable set, but we will not use this concept anymore. But you may see that there is geometric applications in this area of a Finsler geometry. Then we provided an idea of the Stefan-Susman theorem, and the main idea was to present a candidate to be the orbit space. So it was the adjoint of X that essentially is the induced vector field by the adjoint map. Okay, we check that this was a natural candidate because the diffeomorphism sends singular distribution to singular distribution. We define a natural candidate to be a plane. Check the tangent space of this plane was in fact this intrinsic object, and then we glue planes. So after that, we started to talk about the main topic in this lecture, that is the singular Riemannian foliation. A singular Riemannian foliation is a partition of, is a singular foliation such that each geodesic starting perpendicular to a leaf stays perpendicular to all leaves it meets. So it, if you start here orthogonally, then it should meet all leaves. This was equivalent to say that they were equidistant. Again, a good example to keep in mind was an isometric action. Okay, an isometric action, then the partition of M into orbit was a singular Riemannian foliations. We review a few results about singular Riemannian foliations that were kind of generalizations of classical results that we have for isometric actions. For example, if you consider a slice, the normal space of a leaf, then so if you have here a singular foliation, a singular Riemannian foliation, consider here a slice, that this guy here, the normal space, the exponential of the normal space, then we can induce a singular foliation in the slice, considering all the intersections in the neighborhood, and the singular Riemannian foliation in the slice when we identified via the exponential map. That was also a singular Riemannian foliation. Okay, like isometric actions, we have also stratification. We have this nice property, the so-called equifocality property, that essentially say that the leaves are equidistant and the endpoint map has, the derivative of the endpoint map has constant rank. So we have these things that is a nice picture and happens in isometric actions, but it also happens for singular Riemannian foliation. Although it sounds a simple property, it is behind of several results. This so you travel, you start with a leaf that has trivial holonomy. In the case of actions, we consider here a principal leaf. Consider here an equivariant vector field, and then you take the exponential map of this guy. So when this happens, you can travel here along. There is a set here, actually a manifold that comes from the integration of the kernel of the endpoint map. Everyone in the yellow goes to the same point. If you take another point, take the travel along this horizontal geodesic after the same time here. Then you have another line here, and all those points go to this. So this picture is quite important, and in particular, it says that if you have a principal leaf, you can reconstruct the foliation just taking parallel maps. So every leaf is somehow parallel to the other, even when they collapse. So singular Riemannian foliations has two different aspects. The first one is a kind of generalizations of isometric actions, but it can also be thinking as a kind of theory about propagations and collapsing. We talk then about this problem that the so-called Molyneux conjecture, that if you start with a singular Riemannian foliation, but maybe the leaves are not closed, then we can take the closure of the leaves, and then the partition turns out to be, again, a singular Riemannian foliation. This kind of result is important for our lecture 3, because sometimes we want to study the basic functions. So for a basic function that is a constant along the leaves, it doesn't matter if you have this kind of foliation or this, but the second one is quite easier to do. So that was an interesting result. We talk a little about flows in this metric space, and to say a few words about the topics of Jesus, we also discuss that every leaf space, when everything is compact, is a limit Gromov-Hausdorff sense of orbifold. So one thing that I want to stress today that I didn't talk yesterday is the Frobenius theorem. We saw here in the Susman theorem what was the tangent space of an orbit. It contains the information about all possible Lie brackets of your control system, but it contains extra informations as well. And this sounds a little strange. This didn't happen in Frobenius' case. So I would like to start the talk today stressing that under some technical conditions that we call finite generated, then under these conditions, this is true that if you take all Lie brackets, this turns out to be the tangent space of the orbit. And that is exactly the case of the Frobenius theorem. If you have an integrable regular distribution, vectors that are tangents to 8, then and assume that H is involutive. I just missed the scenes here. Assume that you have a guy that we call involutive. That means the Lie if vector fields are tangents to 8, then the Lie brackets belongs also to H. This is called the involutive. When this happens, then H is integrable. That means you have a regular foliation such that the tangent space of the leaf coincides with the distribution. We will use this result today, and this is kind of a very particular case of Susman theorem. So today I would like to talk a little then about connections, the so-called Holonomy foliations, and give some ideas about Ambrose Singer theorem, since this also a short lecture for students. Why not try to learn something or review something? So the basic material will be this previous paper with Marcelo, Matias, Ivan. And I like this book of Andrew and Bianca Santoros. Bianca is in Münster. Diego, if you don't know Bianca, she's a very clever professor and very nice. I always suggest to visit Münster. And they have a small book about holonomy groups in Riemannian geometry and archive. I will take the ideas of the proof of Ambrose Singer theorem from that. So let us then start the talk today. And I would like to start with a few concepts. I want to review the concept of connections, but we will not talk about connections on fiber bundles. We will talk about connections on Euclidean vector bundles. That means we have a vector bundle, and but this vector bundle should have a metric on the fibers. To have concrete examples in mind, consider, for example, the tangent bundle of a Riemannian manifold. Each tangent space has a metric, and then you consider this union. This is an example of an Euclidean vector bundle. Another example, consider an embedded submanifold in the Euclidean space. Consider the normal space of M, and you have an Euclidean metric, then you just use the induced metric there. This is another natural example of Euclidean vector bundle. So kind of every people who has worked a little with differential geometry saw these two kind of bundles. Maybe they didn't have used this name, but they have saw those examples. So what we call a metric connection is a R-bilinear connection that fulfill those properties. It is affine. That means it satisfies Leibniz rules. Here is the derivative of x in directions of f. It is f linear in the first component, and it is compactable with the product. We can derive inner product. And again, nice examples that we saw in differential geometry. Assume that M is an embedded submanifold, then given vector field that is tangent to M, you can derive using the derivative of the Euclidean space and project. Or if you have a normal vector, this would be our first example. If you are consider the normal bundle, you can derive and project in the normal direction. Okay, this is what we'll call Euclidean vector bundle with a metric connection. Okay, just like in Riemannian geometry or differential geometry, we also have a covariant derivative on the space of sections along alpha. That means we have operation. If you don't know what is a pullback of a fiber bundle, it's okay. Just think this is a strange notation for the space of sections along alpha. So we are considered then vector fields. We are considered then vector fields along a curve. That just means this. Okay. And they satisfy those properties. Just like differential geometry, we have a linear map A and B is constant here. We have a Leibniz rule, and it is compactable with the metric. If there is actually a section in a real section, not just a vector field along a curve, then you can define it, you can restrict. And in this particular case, when your C came from a section, then this new operator, the covariant derivative, coincides with the connection in the direction of alpha line. And we call a section parallel if the derivative is 0. So everything just like differential geometry, but instead to think about a tangent space, we're thinking about a more general object, a fiber bundle. And what more I can say about that in this revision? Given then a vector in your fiber, there is a unique parallel sections along alpha that starts at C0. Okay. We can then define a linear isometry between these two fibers and call this isometry parallel transport. And what we do, given C0, we take this unique parallel section, unique parallel section here, and then evaluate at the time A. Okay, so everything works just like a differential geometry, but we are no longer using tangent space. And Jesus, is there some kind of questions from the students? So far, so good?
I think we are so far so good.
Okay. And the group generated by those isometries, when you consider loops, is called an holonomy group. So we like very much this picture here because it's easy to calculate. When you have a surface and you try and you make parallel transport along a geodesic, then the parallel transport is very, 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 very simple. You just take a vector that if your vector is orthogonal to your geodesic, then the parallel transport will be the vectors orthogonal to your geodesic. If a vector is tangent to a geodesic, then the parallel transport will be along a geodesic will be just the velocity. And if a vector is again orthogonal to a geodesic, then the parallel transport will be just a normal vector. This is a nice exercise that we put in differential geometry. I think that was even in the exam, last exam of the students. So with this simple idea, we see that when we make, there is quite different from Euclidean geometry. Recall in Euclidean geometry, you have here, and your connection is just a D. Now you are considering Tm as your fiber bundle. And the parallel transport, as the name suggests, is just to take constant vector fields. So in the Euclidean case, it doesn't matter how I travel along a curve, you always return to the same point in the same way. So that was the case of a curvature 0. The holonomy group was just the identity. But here, in this case of curvature 1, we have a complete different situation. You given a vector, the holonomy group is transitive. It means given a vector, this black vector here and this red one, I can always find a path, maybe piecewise smooth, such that the parallel transport of this vector send the black one to the red one. So it's a quite different situation. And already in differential geometry, we start to have this feeling that the parallel transport and the curvature are somehow very, very related. So, and these are two opposite situations, and we shall discuss this today. So that was a brief review of what we see in differential geometry. So let us now starting talk more about something that you may not seen, at least not with this name. Let I present what I like to call holonomy foliation. So again, we have an Euclidean vector bundle. That means we have here a metric on each fiber. And we also have a metric on the base of this Euclidean vector bundle. The connection is a metric connection. That means it's compactable, okay? Like the tangent space, like the normal space, if we use the normal connection. And consider here the Sazak metric of A. So maybe I should say a few words what a Sazak metric is. It is in the book of Manfredo in exercises. We love Sazak metric when we study geodesics, flow of geodesics in tangent space and dynamic properties of geodesic. But come on, let us just recall a definition. And this is so important, why not? And so consider here, I will try to make a picture. Okay. Here you have your base P, your vector bundle, and I start with the curve alpha here, alpha. And I have my vector here, C vector here, V. C here, okay, that's a bad name, but right now C is a vector. And then I will make parallel transport of this vector. So I have a curve of vectors through parallel transport of these guys. Alpha restricted from 0 to t. So we have a curve of vectors. So a curve of vectors lies on EA. So you have this guy. Now you take the velocity and take then, I will call this curve the lift of alpha. And I take the velocity of it. So the space generated by those guys give you a distribution H. So here you have a distribution H. So every time you have a connection, you induce a distribution, a regular distribution in your fiber bundle, okay? You have a regular distribution induced by your connection. Okay, now I have the foot point of your fiber bundle. That means if I have a vector with foot point P, I just send it to the foot point. And I want to create a metric G on your fiber bundle in the following way. For first of all, so what are the properties? First of all, the derivative of P restricted to this distribution 8 induce an isometry to B. This is an isometry. Second, I would just define 8 as orthogonal to the fibers. And what will be the metric on the fiber? The metric on the fiber, is just the metric on the fiber. The original metric on the fiber. Okay? So when I demand those three things, I have well-defined a metric on A, okay? So this is a metric on A such that the foot point map turns out to be an Riemannian submersion. And this metric is the so-called Sazak metric. As I said, the Sazak metric is a very nice metric. We love Sazak metrics in tangent space because geodesic flows preserve the volume of Sazak metric in tangent space. So when we want to see the geodesic flow is Poisson stable in the unitary tangent space and the dynamical properties like that, we use Sazak metric. So Sazak metric, the volume of Sazak metric also coincide with the pullback of the simplex volume through the Legendre transformation associated to the energy. So we love Sazak metric. It's always appear in tangent space, but we can actually do for every vector bundle with an Euclidean metric and compactable connections. So this someone has some questions? Yes, everyone is free to ask questions. After all, this should be kind of short course. We are a little limited with the time, but anyway, is to try to give ideas, concepts also to the students and results. We try to learn something, so you should make questions. And I try to learn what I'm talking, so maybe I make questions to myself. So far so good. So weit, so good. Then you have the Sazak metric. And now we define the holonomy foliation in this way. We say that two vectors in your fiber bundle are in the same leaf if they can be connected to one another via compositions of parallel transport. Let me show this nice picture that is in our paper. This was a picture of Marcelo draw this picture. So we have here a vector where have curves in the base, then you can make parallel transport, and we allow even smooth piecewise smooth curve. So we make a parallel transport here, then a parallel, then continue to transport. We have alpha here, then we make parallel transport. So in this way, a leaf is then the set of a leaf through V. This is this holonomy leaf through V. Is we fix V and make all possible parallel transport, and then I'm just say to you, this induces a submanifold. Why this is an immersed submanifold? First lecture, Susman Theorem. So you can consider those small curves piecewise, very small piece of those curves as a line, integral line of vector fields, induce vector fields, so you can think about parallel transport as a control system, geometric control system, and therefore this leaf is in fact an orbit. So by Susman theorem, this guy is a manifold. Let us now have, it's a little difficult to draw R4 and the big dimension. So in this dimension, I zip the information of the fiber bundle. I wanted to stress a little the information of the bases. Now I do the opposite. Okay, now Marcelo was perfect. He continued to do both things. This is the base, this is the fiber bundle, but here he wanted to stress the following. If I consider a loop, that means I make a parallel transport of a V and return to the same foot point. But as we saw, for example, even the case of the sphere does not mean that we should return to the same vector. So when you start with V and make parallel transport, we may go to other points. So the holonomy leaf intersects the fibers not just in points, but it may have several intersections. Actually, they intersect the fiber in orbits of the holonomy group. We have a group here. And here is something that we hope to give a few ideas today. we may have to be a little quicker in the proof, but anyway, we will see briefly ingredients of the proof that say that this guy is in fact a Lie group. This is the preview. And so the holonomy foliation intersect the sections, the holonomy foliation intersect the sections, and the intersections are again singular foliation and the orbits of an isometric actions. And this is a very, very nice example of a singular foliation that we should keep in mind today. Yesterday, we talked about isometric actions. Today, I want to talk about this kind of example. And I want to use this example already to establish some terminology. Recall, a slice is the normal exponential map. When I take the Sasaki metric, fix B, then AB is in fact the slice of the foot point here, the foot point B. The slice that is the exponential map with respect to the Sasaki metric of the normal bundle B. After all, B is always, it is also a leaf of the holonomy foliation. That is the slice. Okay, so the fiber is in fact a slice. We have the intersection of the original foliations in the slice. In our case, they are orbits of the holonomy group. We are just accepting right now that this is a Lie group. And as I recalled before, this will be an infinitesimal foliation. That means via exponential map, we can send this guy to a singular Riemannian foliation in Euclidean space. That is clear in this example, because in this example, the so-called the F infinitesimal foliation here are just orbits. I will call this group just H. They are just orbits of the holonomy group for O, V, and B. So this is our infinitesimal foliation. Since this is an isometric Lie group, the orbits are clearly a singular Riemannian foliation. So we are reviewing what we saw yesterday in another kind of example. I started to present a few definitions that we will need tomorrow. We will say that F is infinitesimal compact when this infinitesimal foliation is compact. Do you have examples? Yes. If you consider your vector, your Euclidean vector bundle as the tangent space, then we learn that the holonomy is in fact compact. If your manifold M is an embedded submanifold in an Euclidean space with the induced metric, and you consider the normal connections, we know due to Olmos, a very clever guy, that the normal holonomy is also compact. So we learn in differential geometry, we have two simple cases where this guy is compact. We call that infinitesimal homogeneous when the infinitesimal foliation is homogeneous. That is, every holonomy foliation, it doesn't matter which kind of vector, Euclidean vector bundle that we have, is infinitesimal homogeneous. And as I just said, there is two classical examples of orbit when holonomy foliation is an orbit-like. When your Euclidean vector bundle is the tangent space, then the holonomy foliation is orbit-like. When your Euclidean vector bundle is the normal bundle of an embedded submanifold in Euclidean space. Then the holonomy group, then your holonomy foliation is orbit-like. So holonomy foliation was behind your lectures of Riemannian geometry. Maybe you didn't saw in this way, maybe you didn't call it holonomy foliation, but it was there. Every time when you have a connection compactable with your vector bundle, you have this object, and this is a singular foliation. This turns out to be only regular when the holonomy is somehow trivial, or at least the connect components of the holonomy are trivial. Okay, and the holonomy foliation is quite important for the general theory. So, and that is something that I want to talk now. I want to spend my last 15 minutes, I guess, sketching the ideas behind the proof of Ambrose Singer theorem, that is to explain why this guy is in fact a Lie group. But here I started to put this nice example that we'll use tomorrow. So, Jesus, how are you? Some questions? So far, so good. Do you have questions?
On this end, we are doing okay, I think. Are there any questions in chat?
You and Diego and we are understanding what I'm talking about. At least we three are understanding what I'm talking about. If yes, that's okay. 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 So we have this. And now I want to explain or give a sketch of ideas, ingredients, why this guy is a Lie group. So I will give my definition of a tensor curvature. It's just like in Riemannian, when your fiber bundle is tangent space, we can just write it like that. I use these conventions. I know this is not so common, but I like this convention of a Manfred book. He used it from Chern, and Turner also used this kind of convention. So I use this kind of convention. So sorry, but I'm a Brazilian guy, so I like the book of Manfredo. So we use this convention. And as we saw, we saw that in Euclidean space, parallel transport don't care how I travel along curve, but in a sphere there is a complete different situation. So something that a few students learn and several others never saw is that in fact we can have an interpretation of your tensor curvature in terms of parallel transport. We will consider a very special kind of parallel transport. We do the following. Let me first try to make a picture, then I will present a proposition. But I will consider now two vectors, fields. One is A, the other is A2. So to the pleasure of Diego, yes, those guys will commute. So something that commute finally. And those guys lies on B, the basis of your A. And they are orthogonal. They are orthogonal there in the metric of A1, A2. They are orthogonal at least in your point P0. So this is our situation. I will do the following. I have the point here. I travel along the flow. I will travel along the flow. I will travel along the flow. If you hate my previous notations, write everything like a Persian guy. It's okay. Today I will write like you guys, a normal person. But I will try the time instead t, I will take a square root here. Then I will travel again now using my other vector field. Now I will put here this point was Q1, the end of the first travel. Then I will return. I will return using what? The same vector field, but opposite directions. And this guy here is probably, I will call this K2. And then I will return, and we'll return with this guy here in, probably I will call this guy K3. K3. Okay, since those vectors commutate, when I make those compositions of flow, I start in the same point and ended in the same point, compose those flows, but maybe the holonomy has changed. Okay, so but everything in this local vector fields in the neighborhood of a point, they are orthogonal in this point, and I travel like that. So what we know in some books, and this actually a kind of corollary of this theory in Ambrose Singer theorem, it says the following. So consider here your vector fields that commutate. They are commutate. They are orthogonal at P. And for fix the S, we consider the concatenations of integral curves. This picture here. Travel, 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 return, because everything is commuting. Okay. Take a little careful, be a little careful. There is here the time is square root S. But apart from that is this concatenations here, the explicit concatenation. So we make a loop that depend on S. Now the loop here, you put the parameter T here. Okay. So we construct loops that depend on S. And so now we make a travel in my loop S. I will call that loop S. We make a travel in this loop, and we can make actually a parallel transport along our loop. We start and end at the same point P, but for each S, we have then an isometry. So we have a curve of isometries of AP. You can think this isometries is a subgroup, maybe not closed, of OA, but a subgroup. We are accepting right now that this subgroup will be a Lie group, but so a subgroup of OP. So we have a curve of matrix elements of ON. So a curve of matrix, and then we can derive, consider the vector, the velocity of this curve. So what is then the curvature? The curvature is the velocity of this guy. According to the conventions that we are using, maybe this is a minus. I guess this is right. Probably with your conventions, this may be a plus. So apart from conventions, this is essentially the idea of the curvature. So in particular, if your curvature is 0 in a neighborhood of your points, this velocity is 0. That means this curve is a point, but and this point is the identity. So we are seeing in this nice proposition that if the tensor curvature is 0, then the holonomy in this path does not depend, doesn't matter how I travel with those S, this is 0. And this also provide an interpretation of the tensor curvature. Okay, this is nice result. Sometimes we have time to explain in lectures of Riemannian geometry. Sometimes we don't have time to present, so why not to present here? I like this interpretation. And this will be kind of a corollary of Ambrose Singer theorem. So here the theorem, Ambrose Singer theorem, consider your Euclidean vector bundle and your linear connection that is compatible with the fiber metric. So the holonomy group is a Lie group. That's the first important thing. This is more easy to understand. I hope that at least the students came, okay, I have an idea how it works, A. And that is a more complicated that the holonomy, the Lie algebra of this Lie group is a guy like that. This is strange, yes and no. This is kind of Susman theorem over again. This is the adjoint of vector fields. So this is in fact not so strange after all. But let us see then the proof of A, and I will say a few words of B. And to understand the proof of A, Jesus, please tell me how much time do I have? We start a little later, but I don't want to push.
Yeah, so we have 5 minutes.
Oh, but okay, 5 minutes is kind of okay.
Okay.
And okay, and so let me present what an orthogonal frame bundle is. For every point P, we consider a frame, and for each frame, we can associate the linear map that sends the canonical vectors to the base of this guy. This is a frame, so this is a frame. This guy is Ci, okay? And OAP is the set of all frames of AP. OA is the so-called orthogonal frame, the union of those guys. So the orthogonal frame is the set of all frames. Very natural object if you think a little about that. You have a natural right actions here. It's just the composition of a matrix with your linear map. And this guy is what you call a principal bundle. You can locally consider this pre-image of this guy. You can see as this guy. You should see, and the P here is if I take a frame, I project to the foot point, okay? So this is our space, the so-called orthogonal frame bundle. You have here a free proper. You don't even need this word because the group is compact. So you have a free action here. This is what we call orthogonal frame bundle. And to understand the idea behind why this should be a Lie group, it's kind of everything we need. Yes, kind of what we need. So let us move on. Let us start then. I will define a geometric control system in your frame bundle. How? I take vector fields in your bases and make parallel transport of those guys. And so I have our B here. It's like just the other picture. But now you have something like this, local at least. And if I make parallel, I can make parallel transport along a curve. So if I make parallel transport along the curve, I make a parallel of this frame here, what induce then a curve of frames here. And so this is a curve of a frame. And in fact, I can induce then vector fields on those in this space of frames. Since I have a geometric control system, I have, by Susman theorem that we saw yesterday, a singular foliation, maybe with different dimensions there, whose leaves are orbs of those kind of flows. Note that the holonomy is just the intersections of the fibers with our leaf. So I will make another draw here. Here is our fiber. This is OAP. And our singular foliations comes from transport O frames. So this guy here, I should write probably with the other column. I would put yellow. Copa do Mundo, Copa do Mundo. So I put here yellow. So and the holonomy group is then the intersection of the fiber with the leaf, or with the leaf. Okay. So this is the opt of the holonomy group. Note also that the holonomy groups are conjugated to each other. This is not difficult to see. That means, in particular, that this foliation is no longer singular, but regular. It is regular because holonomy groups are conjugated. The holonomy of P, it is isomorphic to holonomy of Q. And due to those properties, we see that these singular foliations, the singular part coincide. So also note the holonomy group are isomorphic, so the leaves have the same dimension. So you have a regular foliation, this regular foliation intercepts here and induces these foliations in the fibers. So the orbs are submanifolds. And since this is a regular foliation, this is a weak embedded, a concept that I should not say today what is. But since we have a manifold, we have already proved that this guy is a manifold and weak embedded, then this is in fact a Lie group. So the idea that the students should have, this is easy to see that this is a Lie group. I just use parallel transport of the frame. By Susman Theorem, I have here a singular foliation, but the holonomy groups are conjugate to each other. So then we have actually a regular foliation, and the orbs are the intersections of this regular foliation. This implies at least that this guy is a manifold. And then I use something that is in my book with Renato to check that is in fact an holonomy. And my last, do I have 2 minutes? 2 minutes, I will just sketch the tools that are behind of the Ambrose Singer. It sounds complicated, maybe you demand more than 2 minutes, but I will just say a little about that. So in order to understand the Lie algebra, I like to put everything in differential forms. I write the connection in terms of differential forms, the tensor curvature in differential forms. To my conventions, we have the structural theorem here, that essentially the definition of a tensor curvature. If I have other frame, I have this gauge transformation. That means how can I write omega in one frame and in another frame? How can I write big omega, the curvature, in both frames? So we needed this kind of technology. We needed to put some structure in orthogonal frame bundle. We needed to put normal distribution, GL form there and the kernel. We need to write this guy here, a curvature of this one form, and this one form induce a linear connection there. We have interpretations of this strange object, but it kind of reminds us of this. This is a matrix of one forms. This is kind of a matrix of one form as well. The difference is here we eat vectors tangents to B. Here we eat vectors tangents in this strange space, but no worry about. There is a relation between those guys. Here there is a minus due my convention since, okay? And the pullback of this guy is minus this. The pullback of this strange guy is here. So we needed to introduce this technology. And let me at least say the goals behind in my last minus 1 minute. So to prove the item M, we translate this interesting interpretation in this notation. We say here is something that we understand. Here is something written in these new notations using the curvature in frame bundle. So to check that the Lie algebra of the holonomy group is in fact this, we actually have to work with that. So first we check that this guy is an ideal, and in particular subalgebra of G. We have to check that this distribution is integrable. Then when we check those goals, we restrict our fiber bundle instead to work with frame bundle. Now we work with the holonomy bundle, but it's okay because G is already a Lie group proved in item A. Since B2, this is a distribution that is involutive, we have a regular foliation in this subbundle due Frobenius theorem. Now, to finish my talk, my lecture, now, come on. Now, to finish my lecture, we have these regular foliations, and the curves that represent parallel transport are contained in these regular foliations, and the intersections of these regular foliations are P, but the tangent space of this regular foliation is this guy. So this implies that the tangent space of the P, that is G, coincide with our candidate. So you see, we need a little technology that came from using differential forms, but it's kind of okay. If you spend an hour, you will be able to understand. But the key ideas is, again, use Frobenius theorem and distribution. So again, Susman. So thank you very much for your patience. It's over.
All right, thank you very much, Professor.
Questions you can send me by email.
Well, I guess we have time for maybe a quick question. Does anyone in the chat have a question? Because I have a naive one, maybe for a couple of minutes.
Okay.
So,
Thank
when one
you.
considers
I have to pay a coffee.
So when one considers the infinitesimal distributions, my feeling is that at least in low dimensions, these maybe are classified. Is this true, or like maybe say dimension less than 3 or less than or equal to 3 or something like this?
That's a very, 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 very good questions. I like to lie, but I cannot lie so much, so I really don't know. I'm just started to learning these things about the geometric control theory. I found that a fine hobby, and I just have used this language in a paper about Finsler geometry. All I know is kind of what is written in Agrashev, and until now, I didn't saw any kind of classifications. But clearly, there is several kinds of classifications of a control system, because people like a control system in Lie group. This is quite natural. Okay, a control system describe a mechanic. If you want to try to see how a solid moves, this is you kind of see the space that describe a robot. And I'm not lying. The space that describe a robot is a product of SO3 product R3. We have a metric there that comes from mechanic. Inertia, I don't know how you say that, inertia in English,
Yeah, me
and
neither, but I
the
understood.
cinetic energy. Okay, thank you, thank you. Inertia and cinetic energy, quite nice. We have a natural Riemannian metric in this space, and the people use a control system to move your robot. Actually, I just said that in a class of differential geometry for at least a torus. What is a torus for a guy of mechanic? A torus is, of course, you have your robot here, and you have an arm, and you can move here, and you can move here. So you have then S1, product S1, that is somehow in SO3, R3 two copies, okay? Two copies. Here we have a metric. This is not the metric of SO3, okay? And this is a metric from mechanics, and you pull back this to your torus. So when you are trying to make it small torsions here or acting with the forces, you are actually studying movements in your torus with a different metrics and try to control that. This is a simple idea with just an arm of a torus, but of course you can make the entire robot of that. So classical mechanic make robots and things like that is a geometry of connections and distributions, okay? So people there certainly like to classify some special control system when those vectors are very special. So I guess, yes, there should be classifications. In such particular cases, I have a vector field, a thin system that is a kind of a particular control system in a Lie group. So yes, they should have classifications, but they probably have a lot of hypotheses that in some that actually make sense. So control system makes sense for robot. Control system makes sense for what is called nowadays quantum control. People who do that quantum control are chemistry in Princeton and in Köln. Köln, there is the physicians in Köln do quantum control. Quantum control is control system in unitar SUN, and the robot is control system in these nice guys here with connections and the distribution. So it is curious, isn't it?
Yeah, it's very interesting. Yeah. It's very deep
I
thought.
will send you a paper that say the relation about robots and the Riemannian submersion. I found that very clever.
Wow. Wow, that's interesting.
Dual leaves and the Riemannian submersions and the robots. I found that nice.
Yeah,
To
that
lie
sounds
to
great.
people, it's very nice.
Yes. All right, awesome. So thank you very much, Professor, for the very interesting talk.